Cool, yeah. So good afternoon, everyone. We have a lot of slides, so let's just begin. My name is Ifan, and this is Amit. We're from Yelp's ad backend team. And today we're going to talk about how we use Spark to build a streaming pipeline for our advertising ad form. So for those of you guys who don't know Yelp, Yelp is a website where we connect great local business with people. And usually when our users come to our website, they just come to our website looking for, search for a restaurant, plumber, or mover, etc. So today's talk will divide it into three parts. In the first part, we'll briefly talk about what Yelp adds, and then the motivation behind why we need this real-time program. And then the second and third part, we will talk about two of the key technical challenges for us. The first one will be the sliding window, and the second one will be the state management. So first, Yelp ads. So when users come to our website, when they search for something, we will show our ads on top of the organic search result. This is one of the screenshots that I took the other day. So you can see that user can clearly see the ads on the top, and then they have organic search result at the bottom. So what does this mean as a backend engineer in the ads team? Well, basically it means we have a series of events where when the user first comes to our website, we will see an opportunity to show an ad to the user, and we'll log the opportunity. And then the second, when we actually show the ad to the user, we'll log that as a view, which means we actually show it to the user. And then the user might do another search, so we have another opportunity, of course, and then the view event of that as well. And then eventually, user might click on the second ad, and then you will see that we have three different types of logs. The opportunity log, where we log an opportunity that we can show an ad, and the view log, where we actually show an ad to the user. And then the third type of log is a click, where user actually click on it. So we have three types of logs. And just imagine this events timeline will repeat millions of times a day on our website, and we will log terabytes of data. We already have a daily batch that processing all the data and then generate all the metrics, like number of clicks and impressions, etc. However, the daily batch doesn't meet two of our key business requirements. So the first one is real-time metrics. Some of our more sophisticated national advertisers, what they want is they want those metrics to be there in real time so that they can do more sophisticated operations, like they can adjust their bids in real time, things like that. So they want those metrics to be ready in real time instead of wait for those data to be ready next day. And we also find it's a very good selling point to our small local advertiser, where they can just set up a campaign and then they immediately see the number of impressions and the clicks that the campaign generates for them. So that's the first reason that we need this thing to be a real time. And then the second thing is more in the advertising domain, where most of our ad campaign has a daily budget. And that means that if we do not take them offline after they spend all their budgets, we basically give them free clicks and impressions. And that will hurt our ad inventory. And as a publisher, ad inventory for us means the number of total impressions, clicks that we can give out to our advertisers. And if we give out a lot of free impressions and clicks, that means we don't have enough inventory for the rest of our advertisers, which will hurt our revenue. So to meet these two key business requirements, we designed our new real-time pipeline using Spark. So here is the overall process of it. So all of those logs, the three type logs, opportunity, view, and click, we put them into different Kafka topics. And then our Spark program will basically tail those logs. And then in the next step, we basically group all those events by the opportunity ID. If you remember the previous slides, you will see that for each event, there will be ID attached to it. And some of them have the same ID. And then essentially, after this second step, all those events will be grouped by their opportunity ID. And then after that, we will merge those multiple events that have the same ID into one, so that in later stage, those batches do not need to read three logs, but they only need to read one. And then once we have one canonical log, we will just generate analytics and metrics on top of those canonical log. And at this point, we can just answer questions like, how many total impressions we have, how many total clicks we have, how many impressions and clicks for this specific campaign, what's the CTR of it, etc. And then once we have those, we can just send those results to the downstream consumers, and then all the downstream batches can read those data, and then they can do things like change the bid, etc. So that's our overall process. And next, I'm going to talk about the first key technical challenge for us to implement it in Spark, which is a sliding window. So the sliding window fit here in the second step of our process, where we group all events by the opportunity ID. Some of you probably already familiar with Spark, that you know that in Spark there's already some window operation. For example, like a window, count by window, reduce by window, etc. And we look at those APIs, but we find there are two issues with those APIs. So the first issue is those APIs do not enable us to do state tracking. And state tracking is basically essential to us. Just imagine, for example, in this slide, you can see you have, just imagine there's a timeline there, and then you have all those events coming in as like a string. And then this is your first window, sliding window. And then here's your next one. And those existing API, what they do is they will just calculate the state from scratch for each window, which for us is kind of like waste of computing power. Just imagine like you need to reconstruct all the state for the overlapping data that you have there between those two windows. So that's the first issue. And the second issue is the current existing window API doesn't support very complex business logic. And for us, that's also essential. For example, here you can see that, so usually we assume that the opportunity, view, and click, they will come in sequence. So the opportunity will come first, and then the view, and then the click. However, in this example, you can see that all the clicks comes first. Maybe there's just something wrong with your Kafka topic where one topic get delayed, and then the click arrive first. And then you have view arrive, and then at last, opportunity. So for such cases, we usually have pretty complicated business logic to correctly join the clicks with views and opportunities. And with the existing API, we find it not easy to do. So our solution is basically we use another API in Spark called update state by key. And for this API, essentially what it does is it will take a update function, and then it will apply that update function on the incoming data string. And this API, essentially, it meets two of the key business requirements for us. So the first one is that since you can define your own update function, so basically you can apply whatever arbitrary complex business logic you have to all the incoming events. That's first. And second one is for updates by key, if you're familiar with it, you know that it has a built-in mechanism that you can drop state for any key value pair, which means that theoretically, for updates by key, you can keep the state for any key value pair for any long time you want. You can keep it for a year if you want, if you have enough memory or CPU. However, it has a built-in mechanism that you can say, oh, after 10 minutes, I don't want to track those key value pair anymore. Please remove them. So that's pretty convenient for us. So our solution just basically use this update by key function to simulate a sliding window operation. And since we use this API, now everything comes down to like how to design your update function. Basically, we have 3 steps. The first step is where for every incoming new events, you need to attach a date time object to it so that you know like when you receive it and then when you can kick it out of the window. And then you also, if it's a completely new event, then you just need to initialize your state for that key. And then the second one is just if it's old state and if it's the attached expired date time is already expired, then you basically need to remove it from that window. And then the third one is of course for any incoming new events, and also if there is already a state there, then you basically apply your business logic to it. So to translate this into code, it looks like this. So this is basically just like high-level pseudocode of our code base. So basically you have that update function, which takes 2 arguments. One is the new list, and the other one is the current state. So in the first step, basically, you check whether there is already a state for the key. If there's no state for the key, then you initialize it, and then you attach a expired date time object to the current state, so you know when to kick it out. And then the second step is basically you check if there's already a state, then is it expired? If it's expired, you just return none. And return none here has some very special meaning. For that update speak key API, return none here means I don't want this anymore. So basically, when Spark detects that, okay, it's a none, and then it will remove that key value pair, which will release all the memory resources. And then the third step is basically, if there's new events, then let's just apply wherever your business logic to the new events plus the current state. So that's procedure code. And of course, everything comes with a price tag. There's no free lunch. So the downside of this solution is that Spark will apply the state update function to all of the existing keys, which means if you have a huge key space and also your incoming data, the updating data are relatively small, Spark is not smart enough to say that, okay, I will just apply this updated by key function to the small data set. No, Spark will apply this to all the key space, which is not really ideal. And well, to migrate this, there's two solutions here. The first one is just please return really early in your update function. If you detect there's no new events coming, please just exit in your update function. And then for those Java and Scala programmers, well, it's unfortunate for us, we use Python. It's not available to us. But for the programmers who use Java and Scala, for Spark 1.6 plus, there's actually another upgraded version of update by key, which named map with state. And in map with state, it does exactly what I said in an ideal situation where it will look at all the incoming new events and only apply the update function to all those keys that belong to the new events, which is much faster. And according to this Databricks benchmark, sometimes it could be 10 times faster. Yeah, so basically this is how we implement sliding window. Instead of using the existing API, we simulated using updates by key. And then next, I'm going to talk about the second technical challenge, which is state management.
So we looked at how we had to go with the update state by key interface as opposed to the other standard windowing interfaces. But things didn't stop there. I mean, in the sense that to get to production, we had to do a little bit more with the update state key, specifically in the context of state management. So that's basically what I'm going to talk about right now. But before we head in there, we just step back a little bit, look at how Spark abstractly represents data pipelines. So it's basically a DAG. And here's a very simple pipeline where there's Kafka on the input side, and then a couple of stages of processing, and then finally a sink on the other end. So when Spark actually executes this pipeline, now at some point there's very good potential for failure. So let's say there is a failure at stage number 3. In the absence of any caching, what it's going to do is re-pull the exact same data from Kafka again, get through the first 2 stages, and then provide the input data to stage 3 so that it can execute. Now, this is a case where these stages are pretty much idempotent and they have no state involved. But let's take the case of update state by key, which is actually a stateful operation, and let's embed it into the pipeline. Now, the pipeline looks very similar, except there's a subtle difference in terms of an implicit dependency there, which is, since it's a stateful operation, update state by key is not only dependent on the previous stage of this current pipeline, but it's actually dependent on the previous state of update state by key as per the previous micro batch that was executed. So really speaking now, if there is a failure, you don't just have to reprocess batch n through the first 2 stages, but you also have to process batch n-1 in order to actually construct the previous state of update state by key in order to be able to do it. But it doesn't stop there as well, because clearly the previous version of update state by key depends on batch n-2 and so on, and so there's like infinite regress there. So what Spark does to actually limit this is it forces you to actually use a checkpointing. So the checkpoint would be to a distributed file store, and you could essentially choose to do it for every batch or like whatever interval you like. So it doesn't have to be done for every batch. But essentially the state gets checkpointed to disk, which means if there is a failure, then you just have to go back to the last checkpoint and then do the processing from there, and then you'll be able to get back the history. And it's basically bounding the amount of memory and history that you need. So this is essentially what happens with checkpointing. And the other benefit is beyond just being able to recover state for a failed state, you can also actually reconstruct state for the entire application failures as well. So checkpointing gives you a little more than just stage-level failures. So you can actually rerun an application and then recover state back from the disk, and then you could resume from where you left off. So in terms of a flowchart, it would look more like this. Your application starts. You actually tell Spark where the checkpoint directory is, and then Spark will take a look there, see if there's any kind of recoverable state there. If there is, then it could just recover it from there, and your pipeline will resume from where it left off. But if it's the first time you're executing this pipeline, then clearly you have nothing in your checkpoint directory. So in which case, you just set up a fresh pipeline of your own, and then you start the pipeline, which eventually at some point will checkpoint, and hence you will have recoverable state in the directory. And in terms of code, it will look something like this. So you have a main program. You have the get or create, which is the API where the forking happens. So you can provide a checkpoint directory where it can look into, and if there is recoverable state, it's going to get it back. But if it isn't the case, then it expects a custom function from you, in this case, create SSC, which would look something like this, where you essentially set up a whole new pipeline. So you're setting the checkpoint, and then you're setting up your pipeline, and then returning your streaming context so that the pipeline can actually be launched. Now, all this looks good for the most part, except when you start thinking about production systems. So let's talk about what exactly happens during the checkpoint and recovery process. So the checkpointing and recovery process looks something like this. So what's really happening is your objects are serialized. So in the Python world, which we are, it gets pickled, and then there's another level of encapsulation that happens on the JVM side, and then eventually gets to disk. If you're on JVM, then you just get the serialized objects one step less, but it's still the object that's serialized and onto disk. So what this means is that during code deployments, any code changes, especially breaking code changes, there's no way to actually recover state from disk anymore. So you either start afresh or you do something else about how you can recover the state from where you left off. So, well, the biggest reasons why this is indeed the case is that these are all like working at the RDD level, where for Spark, your data is basically a black box. So there's really no way to manage the schema cycle. And so that's where it stands as far as using update state by key, and especially in the RDD context, is concerned. So what we chose to do in order to actually recover state is to actually use replay. So essentially what we do is when the application restarts, we try to go back far enough that the state can be completely reconstructed, and then replay the data, and then the state is back, and then we resume from where we left off. So the natural question, of course, is how much to go back, because how do you know that the state is completely back to where it was? So one of the things, key observations in our case at least, is that the update state, the events that are in the bags in the update state by key actually have a one-to-one correspondence to the original Kafka events. So there's no like merging of events or any of that sort at the point where the data is in update state by key. So like you can see, event 15 here essentially mapped to event 15 there. There might be some fields that have changed within and such, but there is like still a one-to-one correspondence between the two data sets. So what this really means is that if we really knew the offsets of these events in update state by key, then we know like how much to rewind back in Kafka. So what we did was essentially, first of all, propagate this Kafka metadata all the way through in the pipeline to update state by key, so that each event actually has awareness of the partition and offset that it corresponds to in the original data source. So now we actually have information in there to actually figure out how much we can replay when we have to restart. And then as a subsequent step in every batch, what we really do is find the minimum offset across all the partitions, or cluster topic partition really, because there are multiple data centers and multiple topics from which we're consuming. And so once you have the minimum offset, then you know the oldest event per partition in the update state by key state. And then we commit this to Cassandra and external storage, essentially, so that we can actually recover from there. So when the application restarts or after deployment, it would look more like this. So the application starts, it fetches all the offsets from Cassandra. And now we know the offsets from where we need to actually start the pipeline. And then the pipeline is started from there, and it runs. And it runs through all the old data. And then eventually, the state is reconstructed. And then it starts processing new data. Now, clearly, the side effect of this is there are duplicates, because we have already processed the old data before the deployment. And now that we are, again, starting off and going back to where we had already processed data, we will have duplicates. Well, one of the things was that this is not the only case where you have duplicates. Like, you have to be prepared for duplicates in any case in the pipeline, because you could have stages that fail, and then they recreate their data, which eventually has to go to some output storage. And so, and also the source data itself could have duplicates, like Kafka could have duplicates. And so we already had deduping stages built in order to tackle those other situations, which then just doubled up for this as well. So essentially, we have unique IDs per event, per output channel, and then we have a deduping stage to do the deduping so that we have exactly one's output on the output side. So some of the downsides of this approach essentially is clearly that you have to handle a lot of data volume in the beginning. Like right after deployment, you have to essentially catch up and then get to real time. So in our case, for example, we run 2-minute batches, and then we have about 20 minutes of rewind or replay to do. And so clearly, we have 10x more data to handle in the beginning. So there's clearly a burst of activity that need to be handled and then caught up on. And the other thing is also, we're pretty much, at the moment, limited in terms of playback. So right now, we're replaying about 20 minutes of data, but there are clearly use cases coming up where we might have larger windows to deal with, so like 3 hours or whatever. And so that's clearly not something that's going to scale going forward. And so looking forward, we are looking at, well, we've definitely been considering like externalizing state entirely, which would be kind of sad, given that, which would mean that we would do a lot of work outside of Spark, even though we would be using Spark. But given the kind of goals and what's happening in the structured streaming front, there's some hope that we may not have to do that, and maybe there is a solution that will come up in the near future. So in conclusion, well, if you have basically to deal with out-of-order events, and especially in production environments, then and you're in the Java or Scala world, then yeah, map with state would be an option for you. If not, then update state by key is the alternative. And of course, you have to keep in mind that in either of these cases, state is not really carried over to deployments, beyond deployments where code changes or schema changes happen. And maybe structured streaming could be something that might be a near future option for us. Before I close, just wanted to mention that we are hiring across the board in Spark, but also for other technologies and other kinds of skill sets. So if you're interested, do come talk to us. You can also check us out on many of our blogs, and also open source projects that we do on GitHub. And finally, there is a talk on machine learning and how it's used in the targeting area by a sister team tomorrow. If you're interested, definitely you should check that out. And you could also drop in at our booth in the expo hall. Thank you.
Cool. Let's give them a round of applause. Great. So we have a couple minutes for questions. If anybody wants to come up, just walk up to one of the microphones, and I'm sure they'll do their best to answer it.
Do you have any sample pipelines on GitHub? Any sample pipeline published to GitHub? Sample code, reusable?
Can you actually get...
Anything reusable for community on GitHub? Like any repo
Oh, I see.
samples?
Anything to share, like open source wise or otherwise? Not at the moment, but we can talk about it if there is any interest in there. Yeah, but nothing at the moment now.
I had a really quick question. Why did you decide to sort of stick with Python as opposed to jumping to the JVM? Like, I imagine there, like, you take like a stability hit as well, or potentially, right? Because you have to serialize into Python and do that sort of mess. And so I'm just wondering about that trade-off and how you guys made that decision.
So you're talking in the context of state management, or?
Yes,
Like
exactly.
Okay.
I mean, either world, I mean, you still have to deal with state, like across deployments. I mean, you don't, it's not like one has the solution that the other doesn't. And so, yeah, I mean, it wasn't like the other one had a solution, so it didn't really, I mean, at least that was not a factor that made any difference to us, essentially, yeah.
You mentioned that you mentioned that you are running a 2 minutes batch, and you rewind to for 20 minutes, last 20 minutes in case if you want to recover. And how much time it takes to complete one micro batch in your application?
You mean for the bigger batches, essentially?
No, to complete one micro batch, right? How much time it takes to complete your micro batch?
You mean like computer one micro batch?
Yeah,
how
one
much
micro
time
batch.
For us, it's like just 1 minute.
So 1 minute?
Yeah, just
Okay.
about 1 minute. We would give a 2-minute window, but it actually just take a while. Like usually it just take like 1 minute to finish.
So that means if you wanted to rewind and catch up to the current state, right? So how it will take maybe like 30 minutes to pick it up to the current
So
state?
what happens is that we actually don't use any back pressure. So basically after the deployment, the batches are actually bigger. So they're not, one of the things is that the overheads are lower when you have more data coming in. Like you have like bigger batches to process pretty much. And so what we see is that even though the data is 10x, it only takes about 4x the time to actually process it. And so that actually gives us a little bit of a headway in terms of like being able to catch up.
Hey, if everybody could keep it down while you're leaving the room, just be respectful of the speakers and questions and that sort of thing. Thank you.
Yeah, so you mentioned in the regular case you do replays, but in the successful case, do you actually commit the offset to Kafka?
Sorry, can you repeat that?
So you mentioned at first about replay,
Uh-huh.
right? And you keeping the offsets with the data. But if everything were to be processed successfully, do you actually update Kafka to commit the offsets?
So essentially there are two sets of things to deal with. One is like how much have you consumed from Kafka at the moment? But what we are doing for, what we're committing to Cassandra is really like what is in the state, like within update state. Like so essentially what happens is like, so there could have been an event that came like 10 minutes ago that is still going to be in the state. Although we are actually like right now consuming data from like say this minute. And so what's in the update state by key state is really like events which could be like potentially much older. And so what we're really storing in Cassandra are basically offsets based on those events, like essentially the oldest of those offsets.
Right, but do you call the Kafka API to commit the offsets so that it remembers what it is, or it's up to your application?
You mean to reconstruct the state, or?
Yeah, so when you're running the update by state, so Kafka is pumping messages to your application, right? But then as you process those applications, do you update the offsets, or that your application is managing the offsets totally?
So the managing of offsets only across deployments. It's not like while the batches are running. I don't know if that's what you're talking about.
Okay, I think what you're saying is if you do another deployment, then then the replay comes into play. Is that the case?
Yeah, I think it's only if the correct me if I'm wrong, but I think basically it's only if when the applications start, that's when the offsets are actually relevant. So that you'll pass along those offsets to the new deployment, and then that's how it goes about recomputing the state. But during the processing of an application, it doesn't actually do anything with the states besides basically having Cassandra be the state management about the state management.
Yeah, okay, thank you.
Thanks.
All right, with that, let's give them another round of applause.